This, as ever so often, started out as a question. How would you build some audio-reactive particle setup, such as this here in the background? And while not exactly the example that we've been shown, I think we're getting pretty close here. The example in question, by the way, was this, a piece called Oscillate by Daniel Sierra, which apparently was his master's thesis, I think, but I'm not sure. So a really great piece, even though it's almost 10 years old at this point. And I wanted to create my own take on these waveforms that shape, depending on the audio level that's coming in. And when we look at a frame from the final animation, let's break this down into the few elements there are. There is this line from which the particles are emitted and which is driven by the audio. And it's got a few auxiliary lines or secondary lines here, just as a design element. Then we have the particles, in this case rendered as circles, might be triangles, squares, whatever you like. And around each of those particles, we have this tiny arc, this circle sometimes. And this takes down from being a full circle when the particle is newly born, when it's very young, to almost being non-existent for older particles. For example, as this. And also you can see that the particles shrink down over their life. And finally, we have those vectors, those lines that point to the direction that the particle is moving, indicating that particle's velocity. And also the length of that line is proportional to the particle's speed. All this has been rendered in a really flat look, using an on-camera flash-like lighting, projecting those shadows on the backdrop. And it's been rendered using Octane. So let's go over these elements individually. The first thing I want to build is the audioreactive line, from which all other elements are emitted. So in Houdini, starting by dropping down a geonode, diving in there, and dropping down a line. Non-surprisingly, let's point this into the X direction, like so, and give it a length of 2 with 256 points. So here we can see we have this finely subdivided line when we enable point display. Next, I want to select the points that I want to drive with the audio. In my case, I want to drive the very first and the last point. And in this case, I'll select those points manually by dropping down a group node, wiring this in, setting its type to be points, call the group pin, because those are the points that I want to pin in my simulation, and then animate. And then let's put point 0 and the last point, which is the point number -1. So 255 in there. So now you can see with the display of those orange points here, I got the first and the last point selected into this pin group. Next, I'll need an attribute onto which I want to store the audio's amplitude. Let's create this using an attribute create. I want to create a point attribute that is a float and has a default value of 0. That's fine. Let's call this one audio amp. And now we're already at the point where we want to bring the audio. We're going to do so by using a CHOP network, a channel operators network, which is a rather old school part of Houdini, which in an abstracted view does signal analysis and processing. That means it takes in a time-dependent signal, such as an audio signal, for example, and then applies different operations onto that signal and spits out a value over time. So let's dive into this CHOPNet here, and the results of this signals that we're working on the CHOPNet are displayed in the motion effects view here. So we don't have any signals in here. Let's take care of that by loading in a file using a file node and pointing this to an audio file, which I pre-recorded and prepared. So let's click here and navigate to our respective folder and select the audio file here. Now to view this file and this signal curve, let's set the view flag here, and you can see this is the audio that we brought in. And you can see it goes from frame 1 to frame 400 and something. So let's adjust our project settings accordingly by clicking down here, setting our FPS to 25 and our frame range to be between 1 and let's do 450 for good measure. To this node, let's just attach a null, call this one out, set the view flag on this, and you can see the color in the display now changed. That is because in CHOPS you can display multiple curves by setting multiple view flags, which then get overlaid into the viewport here. Currently I don't want that, so I'll just disable the file view flag and just work with the out here. Let's just try and taking this intensity here, this audio amplitude, back to our subs level and writing it onto the points. And for that I need to know that by middle mouse clicking on here, I have two channels in this CHOPNet setup. One is the right and one is the left stereo channel, which in this case doesn't matter because it's a mono recording from a single microphone, so both channels should contain the same values over time. Let's go up one level, and after the attrib create, let's drop down a channel node, which is used to import data from a CHOPNet into the SOPNet. And let's go to the scene view. So this is executed and immediately results in an error and tells me that it has not got any CHOP input. So let's point this CHOP here to the out node we just created, this one, still erroring out. So now Houdini informs us that the channel TX, which we're referencing here, is not found. So what this weird syntax does here is it tells Houdini that it should map the values found in the channel TX, TY, and TZ, so 3 channels, to a point's position X, Y, and Z. So instead, let's map this to audio amp, the attribute we just created up here, and let's use Chan 0, the first channel here. And let's have a look at the geo spreadsheet here. And what we're seeing is that Houdini by default is set up to import this signal that's varying over time in a way that the first sample of this signal is written on point 0, the second sample of this signal is written on 2.1, and so on and so on. If we do not want this, we can set the method to animate it, and then we're getting error again, because now Houdini tries to replace the last number or add to this last number here a frame counter indicating which channel goes onto which point. So in this case, we're trying to add 0, 1, 2, etc., etc., etc. to this here, which we don't want. Instead, let's just delete this 0, and we're still erroring out because now we're creating channel 0 on point 0 and channel 1 on point 1, but we do not have a channel 2 for point 2, etc., etc. So instead, let's run this only over the very first point, and now we're finally getting somewhere. So in the geo spreadsheet, the audio amp that we're seeing if we hit play is only written on the first point here, and it's varying over time, going negative and positive sometimes. Let's switch the real-time toggle and just hit play to see this audio signal oscillating. So now I want to take the first and the last point and move them up and down according to the value stored in this audio amp attribute here. Could be done different ways. In this case, I want to use 2 point triangles, one running over the first and one running over the last note. Let's start with the first note here, and I want to simply tell Houdini to add to my point's Y position the value stored in audio amp. And maybe let's add a slider to dial in the amplitude, the magnitude of that, by multiplying it with a channel float. Call this one audio amp. Create that slider, and now maybe let's just set it to 1, highlight it, and see if that did anything. And yeah, we can see this point jumping around as soon as we're hitting some waveform in our signal. Let's just copy and paste this down here and do the same thing for the last point with the point number 255. And now if we skip through this, nothing is happening because here on the last point, we do not have a value other than 0 written into audio amp. So let's just access our very first point's audio amp by using the point function like this. And now we have both points animating here. For the last point, just in my experiments, I've found it good to dial back this amplitude a bit to 0.05. And for the first point, I dialed this value into 0.5, like so. So now this is the animation we're getting out of this. Now this animation seems very nervous. And that is because when we go into the chopnet and display the curve here, this is an audio signal, so it moves around very quickly here. So let's use chops for what it's good for, filtering the signal and turning it into something that moves a bit slower. In this case, using an envelope. Goes in between here. And for now, let's also visualize the original incoming file. Zoom in a bit, and you can see in the green line what the envelope does. Let's set its bound to signal power, and let's smooth it out a bit by increasing the envelope width to 10 in this case, giving me these smooth undulating curves here. All right, back to our geo level and our scene view. And if we frame this here and hit play again, you can see this is now undulating a bit slower. And also it's only undulating upwards because again, when we have a look at our signal here, we now only have positive values. Remember, the green curve is what we're looking up. Let's maybe put a group around those two nodes here to indicate that the channel is referencing this chopnet here. And now let's use those animated endpoints on the line to put this into a Vellum simulation using a Vellum hair constraint first. And in here, in this constraint, I want to set up the pin group. So I'm going to select that point group we created on the pinpoint slot here and check match animation. So this oscillating points will influence and drive the Vellum simulation. For that simulation, we'll attach a Vellum solver. Let's just reset this for now and dial it in a bit. So under the forces tab, I want to get rid of the gravity, just set that to 0. I don't need any wind, but I want a bit of velocity damping. 0.1 was the value that worked for me. All right, let's save and simulate this. And that is working in theory. The only thing I changed for the final setup is increase the substeps to 2. And that still is working nicely. Let's just get rid of the point display here. And on our viewport settings, hitting D over the viewport, let's go to scene and increase the anti-aliasing samples so this line is drawn a bit smoother. Let's go to maybe frame 75 and take care of creating those additional auxiliary lines. First, let's drop down a color node so we can dial in this line's color. I think I left it at white in this case. Let's drag this out over here because later I'll be working back here. And to create those offset lines, those auxiliary lines, I want to use a time-shifted copy of that line. So let's use a time shift node here and set this one up to be the current frame number -1. And let's uncheck integer frames here. Move this over, wire it up. Let's copy and paste this. And this is 0.5. Again, copy paste this. This is gonna be plus 0.5. And finally, copy paste this one. This is gonna be plus 1. Also, let's use an attrib create to set a width attribute indicating the thickness of these lines. So let's call the attribute creating width. It's a single point float attribute. And for the outer lines here, let's set this to 0.0001. Goes into this one, copy and paste it over here. So those two are very thin. Let's copy and paste this again and increase it to 0.00035. That's the one for those here. Copy paste it over here like so. And the final one for the center line, which is coming straight out of the color node here, which should be the thickest line. So let's go with the value like this. All right, finally, let's merge those 5 lines, just wiring in all those nodes into the merge here. And now you can see I'm getting these 5 lines undulating in time here. All right, last thing I want to do on this chain here is attach a null, which I'm going to call out_lines. One last thing I want to set up is the display here, so I can display the line's thickness. Let's add a camera to our scene by control clicking on the camera icon up here and make sure this camera is locked to the viewport. And let's just reset its translates and its rotates, except for the z-axis. And let's just move this over and maybe zoom in a bit, give it a focal length of about 100. And let's move in, maybe like so. Now to display those individual line thicknesses, what I have to do is go into the geo node where I created those lines and under the miscellaneous tab, enable shade open curves in viewport. And now you can see we're getting an indication of those lines thicknesses. In my case, as these lines are so thin, they just show up in the line's brightness. But if I would go in here and maybe increase this line's thickness, you can see it's showing up in the viewport now. Okay, lines are done. Let's start with the secondary elements by creating those circular particles that emit from these lines here. And to drive the emission of those particles, I want to use the speed at which this center line is moving at a given frame. And for a higher speed, I want to emit more particles at that area of the line. So let's calculate the line's speed, that is the magnitude of its velocity, by using another pointer angle that we attach below the Vellum solver here. And to get the speed, the magnitude of the velocity, which I want to store in an attribute called amp for amplitude, I'm just going to measure the length of my current point's current particle's velocity. And now if I visualize this, I can see in the faster areas here, it's stronger than in those slower areas, for example here. To emit those particles, there would be, of course, different setups and techniques to do so. In this case, what I want to do is turn this singular line into a ribbon and then scatter points onto that ribbon. And to turn this line into a ribbon, I'm going to use the skin node, which can be used to create polygons between 2 lines. So I'm going to need a second line here. In this case, I'll use the time shift trick. Just copy this time shift node that I created here over there and offset that line by -1 frames. So I have this previous and this current line. Let's merge those two together like so. So I've got these 2 lines here and let's wire them into this skin node here. Highlight that and I can see these 2 lines now get turned into a ribbon. The only thing I want to do is, if I highlight the wire shaded mode here, instead of these quads, I want to use alternating triangles like so. So we set this to smooth shaded and then use the scatter node to scatter points onto this ribbon. In this case, I want to use a density attribute. That's the amp that I created from the velocity. Uncheck force total count and increase the density scale quite a bit. Let's go for 8,000 like this. And down here, to make it a bit quicker, you could dial back on the relax iterations and just set them to 2. And also I want to animate the global seed so it alternates over the length of our animation by just using an expression $ff, just using the frame number here as a seed. So now if I reset and replay this animation, I can see we're now scattering points onto this line, or rather onto this ribbon. Let's reset that scene and finally set up the particles using a PopNet, which is just your standard DOPS, your standard dynamics network, just configured, set up for particle operations. That's why it's called POP. It's just a nomenclature here. It's the same network. So we dive in here, are greeted with this, your default setup. We don't need this merge here, and we're just going to work on the particle system here. So the pop object contains the simulation data for the particles and the pop source is there to spawn particles into the simulation. In this case, I want to use all points as an emission geometry. So now if we hit play, we can see those particles will be spawned where those points had been scattered onto that ribbon. However, they fly away forever quite drastically through the scene. So let's fix that and dampen them a bit, as well as add some turbulence using a pop wind here, which goes beneath the first input here. And I want to set the air resistance to 2. So if we hit play now, you can see those particles stop down over time. Also, I want to add a bit of noise, a bit of undulation to these particles by dialing in a bit of noise here, increasing the amplitude to 0.2 and the size a bit. Just values that I figured out when preparing this tutorial. Let's increase the pulse length so it's undulating a bit slower, and also increase the roughness a bit. So now we are getting those particles which are blown around that scene. However, those particles, they live a bit too long for my taste. So let's go back to the pop source here and set up the particle's birth. And in here, I want to dial back the life expectancy to 0.35 and add a bit of life variance, 0.3. So now if we hit play again, those particles disappear quickly. Also, I want to enable the source interpolation and want to set the interpolation method to use the point velocity, making sure that we spawn particles quote unquote in between frames as well. Next, let's go to the attributes here. I want to use the ribbon's velocity when a particle gets born from the ribbon as the initial particle velocity. Just let's increase its amplitude so it's going to be a bit faster. Let's replay this. Okay, working nicely. And finally, back to the birth tab, I want to set up a just born group, which I'm just going to call just born. And into this group, we will only have the particles that are newly emitted, newly born on each frame of the simulation. We want to have that because currently I think it would be nice to add a bit more randomness to the particles' velocities. So when they are born, let's just use another pop wrangle, which goes in between the source and the pop wind. And let's only run this over the just born group that we created. And all I want to do in here is take the just born's particles velocity and multiply it with a random number between 0 and 1. So let's use the random function and use a particle's ID, not the point number. That can vary over the life of a particle depending on which other particles die or get newly spawned into the simulation. So let's use the particle's ID instead of the point number to randomize the initial velocity, resulting in a look like this when we hit play. Last thing I want to set up in this particle network here is the scaling of the particles over their lifetime, which is going to be another 3 lines of vex in a pop wrangle again. And to scale a particle over its life, it would be very handy to have its age as a normalized value. So not its age in seconds or frames, but as a value between 0 if it's born and 1 if the particle dies. And we can calculate that. So let's create a float, call this norm age for normalized age, and it should be equal to the particle's current age divided by the particle's maximum lifespan. And let's also write out this value onto our points, onto our particles. Call it norm age for normalized age. Now I want to use this value here, the normalized age, and remap it to a p-scale. So the particle's p-scale value, that is the particle size, should be equal to a channel ramped version. And let's call this one p-scale over life. And we want to feed the normalized age into it. Let's create that channel slider here. So you can see I can dial in the particle size from its birth here to its death. So let's flip that around. Particle is big when it's born and small when it's dying. And also I want to add an overall slider with which I can dial in the maximum particles scale. So let's multiply this value with the float channel and call this one max p-scale. Let's create that one here, and I have this slider here where I can dial in the maximum size of a given particle. In my previous tests, a pretty small value of 0.008 was good here, so let's just see if that runs. It does, and let's go up 1 level and attach a copy to points node to this pop net, making sure I check pack an instance on that net and just feeding in a sphere for now to visualize those particles, like so. And now you can see when those particles are being born, they are bigger and they scale down over their life. What I could do now is just go in here and dial in this exact curve because a linear fade usually doesn't look as good. And although this is a minute detail, let's just set those spline points to be B-splines. And let's add another point here like this, and maybe add another one here like this. Go back 1 level and let's just replay this animation. Yeah, and that's looking nice. All right, instead of this copy to points, let's just delete that one and attach a null here. Call this one out underscore particles. So now I've got the particles on this slot here and the lines on this slot here. Let's just keep the lines highlighted and go up to the OBJ level and add another geonode and call this one particles. Because for rendering, I want to separate my particles from the lines so that depending on my rendering engine, I can dial in line thickness and line rendering settings independently of the particles and the auxiliary elements which we are about to create. So in this particles geometry, I want to drop down an object merge And in here, just merge the geostream that comes out of the out_particles, like so. And it's in here that I'm going to set up my copy to points, wiring the particles in the right, and a circle that I set to polygon. Let's drag this down, and let's use a division of, say, 20, and wire that into the copy to points left slot highlighted. And you can see pretty much nothing. However, let's unlock the camera from the viewport. If you move the camera around, you can see those individual circles are just pointing into the wrong direction. And that is because copy to points uses an orientation or a normal and an up vector to transform and rotate these individual circles to where it thinks they should be. To fix this orientation, I could just simply go to the circle and set it to be on the ZX plane and then look back through a camera, and that looks almost right. However, when I go to these particles here and display the normal, I see that they do not have a normal attribute written on themselves. And for later, it's kind of important that I have a correct normal and up vector on those particles when it comes to creating those circular arcs around those particles. So let's manually create a normal and an up vector. But the first thing I want to do in here is clean out all those attributes, 45 point attributes, as frankly, most of them I won't be needing. So let's drop down an attrib delete, goes in here, and I want to delete everything, but that's the hat symbol. I don't want to delete the velocity. I don't want to delete the p-scale. I don't want to delete the normalized age, and I don't want to delete the particles ID. So let's just middle mouse on this, only 5 point attributes left, good. Next, let's create this normal and up vector. I want to create the normal so that it always points to our camera that we set up here. So let's use a point wrangle and create a vector, call it campos for camera position, and use a vector interface element, channel V, which we're going to call cam position, and create down here. That's this. Go up to our camera, right click on the translate values, copy parameter, go back into our particles, point wrangle here, and right click on the campos and paste as a relative reference. So now I link my camera position to the slider here, which then feeds it into this vector. Now let's create a particles normal attribute by, from my particles position, subtracting the camera position and scaling this resulting vector to a length of 1 by normalizing it. Like so. So now if we highlight this, you can see we've got our normals pointing away from the camera. So I could turn this around here. Now I've got those normals facing the camera again. Let's also create an up vector. And in this case, I'm just gonna do a cheap trick and just normalize the particles velocity, serving as an up vector of some sort. And now if I highlight the copy to points, let's just get rid of the normal display here, go to my camera 1 and set our circle back to its original orientation along the XY plane. And now we're seeing those circles. However, we're seeing the back face. So the normal's orientation as I had it originally was correct. So now we fix the orientation of those circles and also have correct normals on our particles here. Let's attach a null to this one, call this out_particles. And now let's start working on those secondary elements. So the easier secondary element that I want to work on is the line indicating a particle's velocity. So from this node here, I'll add a point wrangle again. And in here, the first thing I want to do to create lines, let's just zoom in on some of those particles here. First thing I want to do is add another point. So to create a line from each particle, I want to add another point offset by this particle's velocity. So let's first create a slider with which we can drive the overall length of those lines. Let's call this one R for radius and create a slider, which we're going to call radius. Let's set this to some low value here. And next, let's create that secondary point we need for the line by calculating first its position. So let's create a vector, call this one npos for a new position, and it should be equal to the original particle's position plus the particle's velocity times our radius. And now we can add that point. Let's store the new point into a variable called new pt and use the add point function to add a point at the position we just calculated. So now you can see more points, and if we dial back the radius, you can see to which original points they belong to. Let's leave it like that. And finally, create a new line. Let's store this into an integer called new prim and use the add prim function, adding into our current geostream a poly line using our original point and the new point we just created, like so. So now we have those lines for each of those points. Two things I need to take care of for rendering is onto these newly created points, I want to write the original point's velocity, so motion blur is being calculated correctly. And I also want to write the particle's normalized age onto the second point, so we can use it for shading. I'm gonna add 2 lines in between here using a setPointAttrib function to set this newly created point's attributes, such as the velocity of this newly created point, and should be equal to the original particle's velocity. Let's just copy this line here and set it up accordingly as well for the normalized age, like this. And now what I want to do is add a color node down here and use a RAM_from_attribute using the normalized age to color those individual lines here. You can see, depending on the age, they get darker or brighter. In this case, let's just flip it and set this black rather to a grayish value, like so, 0.1 on the brightness. Final thing this needs is an attrib create to set its width, just as we did with the main lines, in this case setting it to a really low value like this. Also, just for good measure, let's go up one level, and on this particles node under miscellaneous, let's check shade open curves in viewport. So now you can see the effect, really small lines now. Okay, let's go back in there and talk about probably the most elaborate thing we're going to do today, which is create those arcs indicating a particle's age around each particle. So let's take, for example, this particle here. This is one of those points coming out of the popnet, and it sits at the position that I called center here, and it's got an age of 0.25. So it's really young. That means only 1/4 of its arc has already gone, and the arc should be ticking down. And the challenge we're facing is manually drawing this arc in Vex around each particle. So how do we go about this? In this case, I decided that each arc will be made out of a maximum number of 36 individual points. That means each point is rotated by 10 degrees around the center here and then connected to form this circle in this case, if the particle is newly born. In our case, for a particle age of 0.25, a normalized age that is, the arc should look like this. So I only want to draw those points and not the full 36 points. For that, I need to calculate each point's position. How do we do that? Well, we take this radius, which will be a manual value to dial in to be arc directable, and then we're going to create a vector, assuming that the center of the particle, just for now, sits exactly at the scene origin, at 0, 0, 0. So we are going to create this green vector here, pointing down by minus this radius value only along the y-axis and doing nothing on the x and z-axis. And we add this vector to the center here to go to this first point. But what about the next points, which need to be rotated around 10 degrees around the center? What we can do is multiply our vector we just created, the green thing pointing down to that very first point here, by something which I denoted with a capital R here. And that, if set up correctly, will rotate our original point by 10 degrees here. So what is this magical capital R? It is this here, this beast. It's a rotational matrix. And admittedly, it looks scary when you write it out like this. However, Houdini has really neat built-in functions to construct such a matrix without having to worry about all these individual entries and the trigonometry behind them. And that's what we're going to use to construct this capital R, this matrix, to rotate this first point to the second position. Now for the third point, what we need to do is take this original vector here and multiply it by the capital R once to get here, and multiply it another time with capital R to get here. And the way we're going to do this in Vex is write down a loop running over the number of points needed to form this arc. And every time the loop executes, it takes a point's previous position vector, for example, for the second point, this would be this here, and multiplies it again by capital R to rotate it another 10 degrees. I'm aware that's a lot, but let's just dive in head first. Let's just zoom into an area here where we see a few less particles and start writing this. So again, we're using a point triangle because we want to do this for each particle. And the first thing we want to do is figure out how many of those 36 points we want to draw out. Let's store this in an integer, call it a max iter for maximum iterations, and it should be equal to those 36 points times our normalized age. But wait, so let's think about it. What are we doing here? We know that we want a maximum number of 36 points on this arc, and that our normalized age goes from 0 when the particle is born to 1 when it dies. So when the particle is born, we would have 0 points on this arc, so the arc would be non-existent. However, when it dies, we would have a full arc. So that's just the wrong way around. Instead, let's just take this normalized age and subtract it from 1. So now, if the normalized age is 0, if the particle is born, we're doing 1 minus 0, that's 1 times 36. So all 36 points of my arc, the full circle, will be drawn. Next, let's create a float, which we're going to call R for radius. Again, using a slider to allow the user to dial in that arc's radius. Let's create the slider and just set up something smallish here. Next, let's take care of that scary rotational matrix. The first thing I want to do is create an empty matrix. So a matrix that does nothing to a point if I multiply a point with that matrix. Let's call this rot for rotation. And to create a matrix that does nothing when multiplying it with a point, we're going to use the ident function. creating an identity matrix, which is a special type of matrix that just does nothing when multiplying a point with it. And now what I want to do is create this rotational matrix from this identity matrix using the rotate function. And I want to create the rotation matrix into my rot matrix. And this rotation matrix should tell Houdini to rotate a point by 10 degrees around the point's normal. Remember, that's the normal we created, pointing away from the camera. However, this function doesn't take in degrees. It takes in the angle as a radians. So instead of writing just 10 degrees, I'm just going to take the radians, which is just another way of spelling out angles of this value here. So now we constructed this rotation matrix called rot, what I denoted as capital R in my explainer graphics. Next, I will set up that initial vector. Remember this green vector here, so 0 minus R, 0. Let's call it PT for point, and set it to be 0 along the x, minus r, remember that's the radius, along the y, and 0 along the z-axis. And finally, let's initialize a list of points into which I will write those newly created arc points, which makes it easier to connect them all together to form an arced line later. So let's create an integer points list called PTS, like so. And now I can write out that loop, counting and creating however many points are stored in max iter here. So let's write a for loop, like this, and let's add a counting variable, call it I, starts at 0. Let's check if I is smaller than the maximum allowed iteration number. And for each iteration, let's increase I by 1. So first thing I want to do is create this new points position that I want to create. Let's call it npos, and it should be equal to our particles position plus this vector stored in PT here. Let's add a point, call this one new PT. Similarly to what we've done with the lines visualizing the speed. Let's set this point's velocity attribute for motion blur using the setPointAttrib function, just exactly as we did on the lines we created. Like so. And finally, let's add this point to the list of points here by pushing it onto PTS, like this. And finally, after all that's done, let's just rotate this original vector here, vector PT, by our rotation matrix, which is simply done in one line, like so. All right, let's just save this and let's see if that worked. Okay, we've got an error. Yeah, missing a 0 here, but now we can see we created those arcs just as singular points around our individual particles here. So let's connect them together to form a line after the loop is done and all those points are created. Let's add a new primitive using the addPrim function, similarly to what we've done with the vector lines, specifying that we want a polyline, and we want a polyline formed out of all those points stored into the PTS list. And now we have those arcs around the points. As we already have the particles at the center of this here, I just want to delete the center points here, making sure we're deleting the particle from which we created all those arcs. To color those, I'll just use a resample node, uncheck maximum segment length, so I don't want to actually use it to resample, but I want to generate a curve U attribute ranging from 0 at the first point of the curve to 1 at the last point, and then use a color node set to ramp from attribute using the curve U. And maybe let's flip around those points and make the last point not totally black, but let's set it to, I don't know, 0.05-ish. So we're getting this color gradient across the circle arc here. And the very last thing I want to do is just copy over this width here to set this curve's width. Okay, let's add two nulls. One to our velocity out. Let's call this one out lines. Like this, copy paste it, wire it up like this, and this one, let's call it out arcs. So we now have three additional elements: the particles themselves, the lines indicating particle velocity, and the arcs indicating a particle's life. Let's just go back into the pointer angle where we created the arcs, and let's increase the radius a tiny bit, like so. And also on this circle here, forming these particles, I scaled it up a bit, like so. So that's the geotree I created here. Let's just highlight the out particles, and to render the lines and the arcs, let's just go up one level, create two more geonodes, call one lines, copy paste it, and call the other one arcs. On both nodes, I want to make sure that under miscellaneous, I checked shade open curves in viewport, and then on the lines, let's use an object merge again to merge in from the particles node the out lines that we just created. And do the same thing on the arcs, this time just object merging in the out underscore arcs that we created. So now you can see I've got all these elements in one rendering here, or rather in the viewport. Okay, let's save this. And finally, talk about rendering this. In this case, I decided on Octane for the render engine, not a really heavy scene and a really simple look I'm going for. So let's set that up. For rendering, just like to close all these tabs, pin this one here, and hit Ctrl T 3 times and set those tabs to be on the out context, the shop context, and the material context. Up here, let's go to my Octane shelf, and I want to click on the Octane and render target, creating an output node where I can set up, for example, the motion blur. For this case, I'll just enable all motion blur options here. And in the shopnet, for whatever weird reason, Octane decided to put their camera imager and render settings into the shopnet. You can set up the render settings, dial in which rendering mode you want, and also the tone mapping and post-processing. The look I'm going for is really simple, so I'm not going to use path tracing. I'm just going to stick to direct lighting. Let's just look through my camera again, and let's just feel lucky and start the IPR. And that is definitely not what I was expecting to see. So let's fix it step by step. The very first thing I'm seeing is I've got a skylight in the background. So let's disable that. On the render target in the shopnet under DL environment, there's a daylight tab, and I just want to dial back the power to 0. So now this is all black. Let's just close it and add some background to this whole thing by attaching a grid to my camera, just going in here, making sure my grid is set up on the XY plane and moving it back a bit so it sits behind my geometry here, which is a bit bad to see. Let's just switch to smooth wire shaded. Let's set it at -5. And let's just dial back the uniform scale so it fills the frame. So that's my backdrop here. Also, as we're having no lights into the scene currently and I want to go for this on-camera flash look, I will create an Octane light by control-clicking on here. And let's make sure we're not looking through that light, but through a camera. Make sure we center our light again so it doesn't sit somewhere weird in the scene, and then wire it up to the camera. So let's have a look at our scene here. Now the light sits perfectly flush at the position of the camera. And let's move it around a bit behind the camera. Settle at this position, bit upwards, like so, and a bit to the right of the camera, like so. Also, under the light tab, I want to make sure this is a circle. And in the shaders tab, under the black body emission, I want to make sure surface brightness is checked. And then let's again look through the camera and start the IPR. And we can see everything is purple and the light is a bit dim. So let's just increase the light's strength and work on the materials that definitely need to be set up. I will just be working with 2 different materials, one for the grid, let's call this one BG by the way, and one for all those elements. Just emulating a very diffuse shading and only importing and using the point colors that we stored onto our elements into the attribute CD. And for Octane, to be able to use that CD or any attribute in shading, we need to expose it to the material network by just selecting all of those 4 nodes here, going to the Octane tab, and in the Octane tab, let's go to the Attributes tab, and under the point vector attributes, let's just select the color diffuse. And now one thing occurs to me that we didn't set a color on the particles, so let's dive in here, and before we create those particles, let's use a color node again, set that to RAM from attribute, and use the after we wire this in here, use the normalized age, and maybe let's increase this black's brightness a bit, like so, 0.05. One more thing I want to do is add a bit of randomness to the scaling of those particles by using an attribute randomize, wiring this in here, and randomizing the p-scale by multiplying it with a one-dimensional, that's a float number, ranging between 0.8 and 1.2. Making sure that I go to the Options tab and check Use ID as a seed attribute, so those points don't jitter. All right, I think we're set up to finally go into shading. Let's head over to the material context and drop down an Octane material builder, copy and paste this, call one BG for background and one diff for diffuse. Let's work on the background first, just dropping down a diffuse material in here, wire it out to the material output slot here. And up here, I don't know, let's dial in some middle gray and increase the roughness of the material quite substantially. Go up 1 level and let's just drag this material builder onto the background. Start the IPR again, and we can see that fixed the material for the background. That's good. Let's work on the diffuse material for the other elements by just dropping down a diffuse material in here as well. And the only difference to the background material that I want to do here is I want to import an attribute again. That is a color, which is called CD. And I want to wire this into my diffuse color of that shader here. Go back to the OBJ level, select those 4 nodes, and under the render tab, let's assign that diff material we just created. Save and hit the IPR, and that still does not look correct. What's going on here? Well, all those lines that we created, they are just being rendered as closed polygons. So let's fix that by highlighting the main lines as well as the lines and arcs, and going to the Octane Fur tab and checking render as curve/fur object. Save again and restart the IPR, and now we can see the faintest touch of those lines, and I think we need to dial in the look of this a bit. So what I'm going to do is, first I'll increase that light's intensity, and then head over into the SharpNet here, and I'm going to set up my render settings and tone mapping as well. So in the direct light, I'm not having any reflections or refractions, so let's set those down to 2. Let's maybe get in a bit of bounce and set the GI method to diffuse. And as we're not having any transparency in here, let's uncheck alpha shadows, and also down here uncheck minimize net traffic for a bit faster IPR updates. I think the maximum samples are not really high that I need here. 512 or 256 should be fine. And let's start refining that look by going to the imager, and in here, let's select a filmic response curve. For example, I'm quite liking those Portois curves, giving a bit of oomph. But you can see now we are tinting this to a yellowish brownish tint. To get rid of that and only take into account the contrast that the curve does, let's check neutral response. So now we're just getting the contrast effect from those film curves without the colorization effect. I still want to dial in that contrast a bit more by increasing this exposure here and decreasing the gamma, making this very, very contrasty here. That might be a bit too strong. Let's go with something like that. And now those whites, they burn out. And to counteract that, compress the dynamic range of that rendering a bit, let's increase the highlight compression, in our case quite drastically, get rid of the vignetting, and also dial in a bit of desaturation when we're converging to white. And I would like to get a bit crispier shadows, so those are very blurred out. I'm going to do that by going back to my light here, going to the transform tab and scaling it down to 0.4 along all axes. So now this light has sharper shadows, but gets darker. So let's go back into our shader tab here into the black body emission. And instead of the 7,000 I dialed in here, let's just go for 70,000. Like this. So now I have this really high contrasty, stark shadowed look. The motion blur is a bit too strong for my taste, so let's go to the camera here, into the sampling tab, and let's decrease the shutter time from half of my frame duration to a 1/10 of my frame duration. Let's reload this, and now the particles appear a good bit sharper. Also in here in my camera, just to make sure that my whole image is sharp, I want to drastically increase my f-stop to say 1 million. And in my SharpNet where I drive the camera, under the camera tab, I want to disable the autofocus here. And I might want to work on the line thickness of those vector lines and of the arcs, but this is my overall render setting for this here. So now as I continue tweaking the line thicknesses here, which I'll do by going into the particles node where I set up those widths here, maybe increasing this a bit. Yeah, I'll just continue tweaking those settings. Gonna provide you with the finalized render file then. But overall, I would call this setup finished. So let's recap what we did here. And we did a lot. So first, we created a line that is driven by audio coming in through chops and then fed through a Vellum simulation to generate those squiggly, wiggly lines here in the center. And then we used the central line here to turn it into a ribbon onto which we scattered those individual points here, which formed the basis of this particle system. And then we used this particle system here to generate not only the main particles as these here, but also a bunch of auxiliary elements, such as these vector lines indicating a particle's velocity and speed, and those arcs indicating a particle's age. And finally, we set up everything for rendering in Octane. The only thing in retrospect I'm unsure about is setting up those secondary elements in here in the particles node. Could have just as well broken out this stream here with a null and then re-imported into the lines and arcs here and set up those geostreams down here. That might have been a logical idea, or more logical idea too. And this tutorial sprung off of a question as so frequently. So please, if there's anything that interests you, if there's anything that in your opinion we should cover, just keep those suggestions coming. We are looking through them. We are reading everything. We just might not be the best in answering in time, but we'll try. And if you folks want to support us, and while doing so even learn more about Houdini using in-depth courses, you might want to consider becoming a patron of ours, as it is through your support that Entagma is possible the way it is. And if you're already supporting us, thanks so much. With a very special thank you going out to Important Looking Pirates, Rafik Anadol and Chris Hebert. Thanks so much. So, as always, looking forward to seeing your artwork. Don't be shy sharing. And until next time, it is cheers and goodbye.